Welcome everyone. In this video I'm going to talk about the tensile curve or stress strain curves. I will start from the basics, so I will show you how a tensile specimen looks like, then how the tensile curves looks like, how we can interpret the data that we obtain from a measurement, and how we can use this data to characterize the properties of the material. And I will also show you an example how to do this. So I will use some data which I measured, and I will go through all the steps, all the details step by step, and show you how to evaluate the data from the very beginning until you get the curves plotted and you get the most important values for the material evaluated. So let's start. First of all, I would like to talk about the sample. I try to draw it nicely, but I'm not sure that I'm able to draw it nicely. But basically, what we usually use is something like this. So we have a dog bone shaped sample. It can be either a cylinder or cylindrical specimen, or it can be something cut from a sheet of metal. So it can be rectangular. It doesn't really matter. We can obtain the same details from both materials, so it is more depending on the source material what you have. If you have rods, then it's more smart to produce cylindrical specimens for testing. If you have, let's say, steel coils, then of course you will use flat specimens and you will measure the flat specimens. But you have your dog bone shaped material and you want to measure it. So let's first go through the parts of the specimen. So let's call these like G. So these are the grips. Basically this is the part where you clamp the material in the tensile testing machine. So you will fix it with at the two ends of the material, and then you start to pull it. And basically, yeah, we have some length, which is basically the overall length of the sample. And then we have another length, is basically the length where the specimen is straight, so you don't include these necks. And then this length is often called parallel length. This is supposed to be an R. And then you try to measure the displacement of the material as precisely as possible. So sometimes you just use the parallel length for the measurements, but sometimes you attach an extensometer to the material which can measure the displacement very precisely. So usually that is fixed to the sample somewhere in between the area of the parallel length, and then this is called basically gauge length. So this is the area, this is basically you measure the displacement between these 2 points, and when you apply force on the material and you start to pull it, then you measure the displacement of these 2 points. And when you do the test, basically you just pull it pull it apart, let's say. And then often they say that this kind of testing method is uniaxial tensile test, because you are just pulling the material along one axis. So this is why it is. So what you get from this measurement is basically two things. One is the load, expressed in newtons usually, or if you have large samples then it is in kilonewtons. In my samples I get the results in kilonewtons. And then you have displacement, then this is usually millimeters. And of course if you start to load your sample, then you have some linear section, and then the sample starts to deform plastically, so you have some kind of parabolic region, and then the material fails and it breaks. So yeah, it will end here. But this is just load and displacement, and you cannot really get any useful information from this material, so you usually use something else which gives you more meaningful values. But the funny thing is that the curve is almost the same, or we can say that it's nearly it's the same basically, but you have different numbers assigned to the points. But what we have here, this is the first what we use, is the engineering tensile curve, let's call it like this. So what you have here is the engineering stress. It's usually expressed in megapascals, and then you have the engineering strain, which has no units. How you get these values is basically the load and the displacement and the dimensions of the specimen. So first of all, if you want to calculate the stress, it's basically what you learn from physics. Stress is force divided by the area, and then the area in this case is the initial cross-section area of your specimen. If you have a rectangular specimen, then the thickness times the width of your specimen. If you have if you have a cylindrical shaped specimen, then you use the area of the circle, or the area of your cylinder. So basically you just calculate it from the diameter. So this is what you get as an engineering stress, and then you can obtain the engineering strain as well. That is also very simple. That is basically the change of the length divided by the initial length. And then this initial length, if you don't have extensometer and you just rely on the displacement of your specimen, then you use the parallel length of your specimen. If you have extensometer, then you use the distance between the grips of the extensometer. So that will be the L0, and then you get the delta L, the change from the extensometer, or the start it again. So L0 either comes from the initial length of the specimen, which can be the parallel length if you don't rely on the extensometer. If you rely on the extensometer, then it will be the initial distance between the grips of the extensometer. And then if you have extensometer, then delta L comes from the precise measurement of the elongation, or If you don't have anything, then you just get the displacement readings from the tensile testing machine. So basically that's what you have. So these are the two important terms, engineering stress and engineering strain. But this is somewhat problematic because it's not accurate. Why? Because you are using the initial values of your specimen, but during the testing the material will change its shape, so therefore the area will change, and you are not getting the correct stress values, especially the stress values for this kind of numbers. So engineering terms are not the best. But then what is the best? So let's introduce the true stress and true strain. So yeah, true terms. So basically they are of course the same units, so nothing changes, only the method changes. So what we do here is we say that the volume of the material or the specimen is constant during the test, and that is of course true. So let's make this statement, which means that the initial volume, so A0 times L0, so the initial cross-section area times the initial length of the material is the same. And then this should be equal with the actual cross-section area times the actual length, right? And first we would like to calculate the stress, the true stress, and it's very easy to calculate it by using this equation. We just rearrange it for A. So let's do like this, and then this will be A0 times L0 divided by L, right? It's very simple. So then we can get something like, let's get the stress. So now in general stress is F over A, right? And then if we want to make it into true, then sigma T equals, let's make it like this, F over, right? And we can still continue this equation, and therefore we get something like this. So you can see that basically you have the force divided by the initial area times the ratio of the actual length and the initial length. So this is some sort of correction. And then we can basically obtain the elongation or the strain, the true strain, in the same manner. So previously in non-true terms the engineering strain was something like this. But then this is not so, yeah, it's not so elegant, right? So we can say that if we just if we just use this L divided by L0 minus 1. Why do we use this? First of all, because we can calculate the engineering we can calculate the true stress in a more elegant way, which is basically the following. So we can use this expression minus 1. So we can use this expression and use this expression, and I guess you see the difference, but we can write like this: F minus A0 times epsilon plus 1. So basically what we have is the following. If you recognize this term, then this was sigma engineering, and then we use this, and this is also engineering. So from the engineering strain and the engineering stress, you can calculate the true stress as well. And then we have to get the true strain. That's maybe a little bit more complicated, but it's not that much complicated. So what we have, basically, we would like to calculate the displacement between L and L0, so the actual length and the initial length. We do it like this, so we integrate the whole thing, which is basically something like this. And then I guess now you recognize this if you use the form. 1 over L is basically a logarithm. I just go through all the steps so you can see the mathematics. And of course you just substitute the L and L0, so you have ln L minus ln L0. And if you see two logarithms subtracted from each other, then that's a division, right? And now you can do some fancy things. So we go back to the L divided by L0 minus 1 again, so this equation here, and we can basically say that, let me write here in the corner, so we said that this was, but this should be rearranged to L, like this. So then we can continue, so ln, and then we use this term L0 times 1 plus epsilon divided by L0. Then just simply, let's make this, if you see, so this is the final result. So you can see that it's very simple to obtain the engineering stress, the engineering strain, and then the true stress and the true strain. And basically these are the 4 most important details or most important numbers which you can get from the tensile test, and these numbers can be used to determine some important numbers for the specimen. So I think we will continue from here on the next slide, and I will show you how to use these numbers in the real life. So let's continue from here. So now we are back with this software which I use to plot and analyze different curves and functions and stuff. And as you can see in the table, I already have all the details calculated. I was testing an austenitic steel, so these are the details of the steel. So you have the load in kilonewtons, and there are a lot of measurement points, and then we have the displacement here. So that was the two things which I was showing you in the previous slide. So if we plot it, I will show you what we get. So let's put the displacement on the x-axis and the load on the y-axis. So this is what we get. I hope it's visible. So we have our linear section here, and then the kind of parabolic section, and then here the material starts to fail, and here it breaks and the measurement is finished. And you can see that from the start to the fracture, the material had more than 5 centimeters of elongation, and then we reached like 15 kilonewton load at the as the highest load. So yeah, this is the most basic, but we cannot really use this material, so this curve, it's not so informative for us. So instead of this, let's first check the engineering curves, which I show you again by plotting the engineering. So if you remember, then we calculated the engineering stress and engineering strain by dividing the displacement with the original length and dividing the so we divided the displacement with the original length, and we divided the force, the load, with the original cross-sectional area. But now we have different terms. So as you can see, we have megapascal now as stress values, and we have like 600 at the maximum, and then we have this engineering strain without any units, and it shows 0.5, which is 50% elongation in this case. But this is still not accurate, as we said. So let me put some other graph here. So I also calculated the true strain and the true stress, which is based on the instantaneous change in the length and the diameter or cross-section of the specimen. So if we go and plot those values, then we can see that we have a bit more steeper curve. Let me enlarge it. And we have larger numbers. And then of course we have larger numbers because if we start to pull the material, then the cross-sectional area will decrease. So if you decrease the cross-sectional area and you increase the force, of course you are getting larger and larger stress values. So therefore, if we compare it to the engineering curve, we can see that it is considerably different, right? But the numbers are more or less close to each other. So we have the true stress, true strain values. We should see what we can do with it. So I will go back to the slides and I will show you some important parts, and then at the end I come back here and I will show you how to do it. So let's go back to the drawings. So first of all, let's start from the beginning. So what you can see, you can neglect this part here. Now it's not important. But what you can see that we have a quite linear section here before the curve starts to deflect, and then we have somewhat linear here. But what we need to know from the beginning. So as you can see that this is linear, right? The linearity basically comes from Hooke's law, which is, if you remember, is F equals K, so some sort of constant, times X, which is the displacement. So if you have a small spring and you pull it with a force, it will have some linear increase in the length. And if you release the spring, then it will go back to its initial length. The material behaves the same here, the metallic materials especially. If you have this, when you have this linear section, which is called the elastic region of the deformation, let's say until it starts to deflect. So you have a reversible and totally elastic behavior. So if you pull the material just a little bit and release it, it will go back to its original length. And then this Hooke's law can be expressed in terms of stress and strain. So we have the stress, which was the F, and that equals with epsilon times E. So we have stress. This is often described by a 3x3 matrix, and then this is also, but this is strain. And now we have a new unknown parameter. It's often called modulus of elasticity, or Young's modulus. This is one of the most important parameters to get from a tensile test. So when you do a tensile test, you have to evaluate this section of the area by fitting basically a linear curve on this section. I will show you how to do it. And by evaluating the slope of this curve, so delta epsilon and delta sigma, you can get the Young's modulus. And this is in the case of steels, it's roughly 200 gigapascal. So I also did this, or I also made this green line here, and I will tell you what it means. But first, so we have our curve. Just to simplify everything, we have this, and then it starts to deflect. So as you can see, so this part, this is elastic, and then this is plastic deformation. What it means: elastic, reversible, and plastic is irreversible. So for example, if you have, let's say, you have a fork and you bend it just a little bit, then you just deform it elastically. So when you stop exerting force on it, then it will go back to its original shape. But if you bend it too much and make it into a U-shaped metal, then that's a plastic deformation, and it cannot be reversed. So I mean, the material will not reverse itself to its original shape. So that's a permanent deformation. So let's go back to the green curve or green line. What I did here, I used the same slope, but I shifted the curve to 0.2 or 0.2 percentage. So in this sense, this is 0.002. This is basically used in engineering fields, but this point where the green line intersects the red line, the tensile curve, it's also called, often called either yield strength, but this is maybe not the best or most precise. But if it's also called proof stress, or it's also called just like RP 0.2. But maybe yield strength is not the best expression. But this is very important, because this number tells you which is the highest point where you can load your material and you get elastic deformation. About this point, the material starts to flow and you have permanent deformation. So now I added another image with some more details and some additional curve. So as you remember, we used this was here, right? But now we are curious about the wall curve, what we have here. So there is another intersection here. Basically what we have here, this black curve, is this guy here, so the derivative of the tensile curve. And then what we have here, the intersection, is called considers criterion. So basically it says that if this equation is satisfied, so the derivative minus the stress equals 0, then about this point, so basically about this point, the necking of the sample starts to, so the plastic deformation is getting unstable. So therefore a lot of people, or basically everyone should, but a lot of people just draw the curve until this point here, and they just discard this rest of the curve. So this is a very important parameter, and you can get it by having your tensile curve. You should differentiate your curve like this, put them on the same figure, and just evaluate your curve. So this is what you get. And then you can get several other parameters. So basically up until this point where you have your failure, you will get the total elongation, and then if you have the stress at this point, this is called the rupture stress, or rupture strength, I would say, strength. And then at this point, it's not so straight, but you get it. This is the ultimate tensile strength, UTS. And then up until this point, from the beginning, you have uniform elongation. Because after the material starts to show necking, the elongation and the deformation is not uniform anymore. And after necking, further straining is basically not giving you the correct stress values, because you have very different cross-sectional area. So this is what you can get from the curve. And now I will go back to the other software and I will show you how to make these things in practice. So we came back to the curve which I showed you previously. So first let's evaluate the modulus of elasticity. So we just need this area right now, and we would like to get the slope between, let's say, 0 and just eyeball these things, 0.0014. So I will try to fit a slope on this section right here. So basically we are just looking for a very simple a times x plus b expression, and then we are going from 0, 14. Actually we can be more precise, and then we try to fit. So we see that there is a fit. So let's say we are satisfied with this linear fitting. So of course you have two parameters of this fitting. You have the slope and you have the intercept. The slope tells you the Young's modulus. In this case it's 143 gigapascals. And then this b-intercept is not important right now. But what is more important, that once we have these two values right here, then we can evaluate the yield strength of the material, or proof stress, 0.2 proof stress. What we do is basically we just need to create a new curve, and how I do it is the following. So I will basically just give a add function. So I just define a linear function a times x plus b, but in this case I will shift this curve by 0.002, and then for the a I'm just using the previously obtained a and the previously obtained b. Well, now it's not so important to have proper values, and of course this should be never mind, it's a bit funny. But what we have here right now is basically what we need. So here we can see where the two curves meet, 300, roughly 301. So the yield strength of this material, or the proof stress of this material, is 300 megapascals. So we can already write down one value, and we are very happy with it. So we can continue. So basically this is the second value. So we know the Young's modulus, or modulus of elasticity, and now we know the 0.2 proof stress. So now we only need the ultimate tensile strength of the material. Now I will cheat a little bit. So because there is one problem which you should know. If you have a lot of data points like me, I have like 5,000 data points, and if you try to differentiate that curve, the following thing will happen. So once you can see, because the points are scattered within a small region, but there is a lot of scattering, so the derivative will go crazy and you cannot really get any useful values from this. So, which I usually do, I discard some values and I just try to reduce the number of points along this curve to 100 or 200. That's fine. Or if you want to do, then basically you can fit, sorry, so basically what you can do, I want to show you a little bit more precisely. You can take a point between the yield strength and between roughly the maximum strength and fit a higher order polynomial on this curve, and then if you differentiate the polynomial, then you have the analytic function. So that's very straightforward. You can either do it, you can even do it by hand, but then the derivative curve will be nicer, but maybe that's not so nice. I don't know which is better. Either you can fit a polynomial on this curve and differentiate that, or you can have this curve, but you just throw away most of the points and keep just 100 or 200 points and fit and make the differentiation on that one. So basically I have the data points here. It's like almost 6,000, not even 5. And I just filtered this. So what I have, sorry, is basically 112 points. So if I plot these 2 points as scatter, you can see that it's a bit more scarce around here. But once you try to differentiate this guy here and try to get the reasonable area, then you have much nicer curve. Of course you still have oscillations, but these are okay, and if you want you can just throw away this kind of, or you can get rid of this kind of oscillations by filtering or smoothing this curve by some averaging method. But now we can use this. So if you remember that we said that d sigma divided by d epsilon minus sigma equals to 0. So basically I already made the curve, so I will show you if I can find it here. So I had my tensile curve and then I plotted the derivative on the tensile curve. So basically what we need, let's just take our pointer, 885, and it's roughly 38 or 37.7 percentage. So the ultimate tensile strength of the material is, or this material is 885 megapascal. So we have our fourth detail, and the fifth detail can be the uniform elongation. It's 37.7%. And then we can also have the total elongation if we want to have it, just reading it by the last data point basically. And the rupture stress also can be read from this curve. So I think we got everything. So we got the to go through everything once more. So we got the modulus of elasticity by using the curve and getting the linear, the slope of the linear section, and then by shifting that by 0.2 or 0.0002, then we got the proof stress of the material. If I magnify it a little bit, well, you can see. And then after getting these two values, so modulus of elasticity and proof stress, then we went back, we made a derivative of this curve, and then we plotted on the same chart or same figure, and by reading the intersection we got the uniform elongation and the ultimate tensile strength of the material, and then if we go further we can also get the total elongation and we can get the rupture strength of the material as well. So a lot of details can be extracted just by doing a tensile test and evaluating the tensile curve. And this is just one step, because you can take the material which you just destroyed by doing a tensile test on it, and you can put it under a microscope, either an optical or an electron microscope, and you can check the microstructure of the material. I will show you some examples of that as well in the future. So I hope this video was somewhat useful, and I hope I did not make any mistakes. If yes, just leave a comment and I will try to fix it as soon as possible. But yeah, I hope it was some useful knowledge for you, especially this practice where I showed you exactly how to evaluate the curve. And if you liked the video, just please leave a comment or like or subscribe or whatever. Just use the knowledge for nice things. So see you in the next video.